Hello everybody, I'm Sunjun Kim from Aalto University, and I'm now a postdoc researcher in the Untitled group. This is the case study which is the part of, in fact, a part of my PhD thesis and under the supervision of the Geehyuk Lee. And this is also a collaborative work with Hancom, which is the Office software maker who produces the Office suite as well. Okay. Raise your hand if you ever tried working on a tablet PC. Okay, great. Many of you are working, and nowadays tablet PCs are getting more powerful, having more powerful processors, and they are now capable of run very heavy productivity apps such as the word processor, presentation, and spreadsheet, etc. However, there is a problem of the screen space when users is using a virtual query on the screen. So, for example, in this case, the toolbar and the keyboard is occupying the screen, and only 1/3 of the screen is utilized for displaying the content itself. So there are many remedies already tried so far. So one very obvious example is using an external keyboard. However, the external keyboard is not always available, and it is an extra device which you need to carry on. The other approaches are using statistical decoding. For example, if the reduced layout is reducing the query layout into 1 or 2 lines, and multiple keys are assigned to one key. And they disambiguate between letters by trying statistical decoding. One extreme of that kind of approach is invisible keyboard, which is recently presented. And there is no keyboard presented, and only the touch points are decoded by the statistical decoder and produce a word. However, they are having out of vocabulary words problem. And if you are working on some specific domain work, then there is a lot of chance that you are dealing with non-vocabulary word, which is the problem using a productivity suite, especially. So our approach is using a semi-transparent keyboard. So the keyboard is sharing the workspace with the contents of the document. And one advantage of this approach is you don't need to use the statistical decoding. So there is no need to disambiguation between the characters. And the other advantage of this approach is you can use some extra keys, such as a modifier functions keys and so on, which is not available on the reduced layout often. However, there are visual conflict between the keyboard and the contents. I only assume keyboard on the text editing context, so I only tested the conflict between the text and the keyboard in this work. So they are conflicting visual attention between the typing the keyboard and the reading the text behind the keyboard. In fact, this is problem of the divided attention model from 1995. And if 2 layers are competing each other, a degree of transparency is key attribute that a user can control. And there is some optimal trade-off point which satisfies the both. So in this case, your design is only changing the transparency level. There are the other approaches that, for example, the multi-blending from Patrick Bowdish is actually trying to assign different attributes to different layers of the contents. So if you're focused on the color of the contents, you can probably read this red, green text, and so on. And if you're concentrating on the luminance contrast between the background and the text, you can read probably once you step back the blur something. So there are 2 layers are overlapping. However, if you are by focusing on the different attribute, 2 layers could be disambiguated. There are several similar approaches that 2 text layers are overlapped and they having different luminance, character, outlining, hue, or font, and motion. So I try to collect as many attributes as possible for designing a transparent keyboard. And those are the results from several interviews with expert designers and the HGI researchers. And I collected that number of attributes which have discrimination, which is believed to help the discrimination between layers. And I excluded a few of them by doing several iterations of the pilot study. So this is my experiment design. So in the first experiment, I tested the effect of the transparency of the semi-transparent keyboard. And in the second experiment, I explored the all possible design space of the STK, which is the semi-transparent keyboard in short. Let me explain from the first experiment. So in this experiment, I tested opacity with different opacity with the baseline design, which is kind of having similar look and feel of the Windows keyboard. So it replicates the look and feel of the Windows keyboard, and it has a similar form factor to regular key sizes, such as that is width of 18.2 millimeter, which is only a 1 millimeter less than a regular keyboard size. From that base design, I changed the opacity, which is the opposite term of the transparency. I changed the opacity and generated 4 different keyboards with having 10%, 30, 50, 70 opacities. 90% was excluded because the user cannot read anything on that condition. So there was only 4 test conditions. And the opaque keyboard was presented as the reference condition. So I mentioned about the visual conflict between the reading text and the typing on a keyboard. So there are 2 tasks, obviously. The read task was given like that. So this is the reference condition, which the text is not occluded by any. And the other one is the keyboard condition, which the text is overlapping with the keyboard. And user was requested to read the whole text. So after user clicks the reading button there, the text appears with the sum test condition of the keyboard. And after user reading all of them, user hit the button again to finish the task. Then the reading speed was measured. The reference condition was the native condition, which doesn't have any visual interference. And the STK conditions were overlapped with the 4 opacity keyboard conditions. And this is the actual footage that the user is performing the task. So after user finished the reading, hits the button again, and then it finishes the task and the speed of reading was measured. The other task is the writing task. In this case, the reference keyboard is completely opaque. And this is the STK condition, which is user need to type on a keyboard overlapped with the existing text. So in this case, I try to maximize the interference between the text and the keyboard. So all the QWERTY areas covered by some random text. And user was requested to type the text as accurate and fast as possible. And the reference condition, user is not interfered by any of the text. So text area is cleaned and the key area is opaque. In STK condition, I tried to overlapping as much as possible so that presented text is also occluded by the keyboard and everything is interfering each other. This is the footage of the real experiment. So the procedure and the design of the experiment is as follows. There was 10 participants participated, and there is 5 keyboard conditions. 1 is the reference and 4 test conditions. And there was 2 blocks consist of the 5 blocks, 5 reading and 5 write tasks for each of the keyboard, and they were repeated in the 2 blocks. And keyboard was presented in the random order to eliminate any kind of order effect. This is the key result. So the y-axis is the reading speed, and the x-axis is the writing speed, which is normalized against the reference condition. So reference condition is 1.0, and the others are the normalized. So as you can see there, they are forming some kind of Pareto fronts, and the 0.5, which means the 50% opacity condition, looks like a most balanced condition between them. We also measure the other metrics such as the error rate, and we make some combined metrics that combines the reading and writing speed. So the harmonic WPM is assuming the user is reading and write the same amount of the text, and the arithmetic WPM indicates the user is reading and typing the same amount of time. And every research says that the dominance of the 50% condition. So we concluded that opacity 50% is kind of most balanced condition between the typing and writing. And as you can see there, the performance of the typing and writing is over the 95%, which is very impressive to the reference condition. Okay, this is the second study. We explored more design spaces. And this is the design toolkit which having a lot of control knobs, which is controlling the brightness of the key and the background. And the other one is the luminance contrast between the key labels and the key. And designer can actually assign as much as key colors as they want. And the other one is the shadow and their offset. And the other one is the font weight, font sizes, and different font rotations to discriminate between the label and the text. And font blur, which is the similar approach to the multi-blending. So we also provided a randomized function to make the designers more creative and not biased by their previous experience. So we recruited 6 professional UI designers, and on the day 1, they generated 5 instances of the keyboard design. And in the day 2, they tested the keyboard with the writing and reading task and picked only 2. At then day 3, they generate 3 more, and day 4, they reduced that into 2 by evaluating them, and so on. Day 5, 6, and 7, and 8. So the final design from each designer is 2 designs, and they are as follow. So expert-driven design, 2 designs per designers, and 6 designers generated 12 designs. And the conclusive facts were founded that there are borderless design, which means that the key shape is disappeared and doesn't appear on those designs. And they usually choose the brighter labels than background, because the text is darker than background usually, and they want to discriminate the key labels by brightening them. And they don't really like the blur design, so they usually use the crisp and unbright labels. So we could eliminate the design space further and only remains the relevant features. So this could be a guideline for who want to design a SDK for future. The performance evaluation was done with the reference and the 12 designs. And we similarly tested the typing and the reading, and they formed the same kind of Pareto front as shown there. And there are 3 designs are forming the Pareto fronts, and they are actually performing, they are included in the top 3 designs in our metrics. So there are A2 design, which is represented there, and E1, D2 designs are apparently the best. And we picked the D2 as the most balanced candidate. So we focus a little bit more. We take more credit to the writing speed. So we picked the D2 as the best design from the experiment 2. Finally, I evaluated the best instance from the both design using a caret position experiment. So because the STK is semi-transparent, so the caret could go behind the keyboard. So I want to test the text entry performance on different caret positions. So I designed the roaming task, such as that. So there are caret positions, and user was requested to type some random words. Type the presented phrase on that caret position. So there were 12 caret positions, and users were requested to remember the phrase and type the word accordingly. So 15 participants were participated and 2 keyboards were tested, one from the 50% opacity condition from the experiment 1, and the other one is the best instance D2 from the experiment 2. And we pre-tested the reading and writing, a similar task to the previous one, and their performance is shown in the table, which is kind of really similar to the reference design. And we tested the position, various positions. So blue means better and red means worse. So as you can see there, write WPM, which means the typing speed, is better at the top 3 positions, and the error rate, corrected error rate, and is getting worse under the hands, which is the bottom left and bottom right of the side of the keyboard. And non-corrected errors are increased, in fact, in the bottom left and bottom right. So users are mostly ignoring the error happen at the positions. And for the bottom one is the raw values, so they are not relative to the reference position. So this is my recommendation of the caret position. So on the blue area, there is okay to use. So those areas, the cursor could be overlapped with the keyboard. And if the cursor is go beyond those positions, the program probably need to scroll up the cursor for a better comfortable position to text entry. We also evaluated the subjective preference of the 2 designs, and in the reading, the borderless design was getting more points, and for typing, the border designs that takes more points. And overall, they like the borderless design. So my final design recommendation is using only the bordered keys for special keys such as the modifiers, and use the other part, borderless design for the other part, which is less occluding the content. And there is slight reading interference, so the reading the context behind the keyboard is not as fast as the reading the clear text, but it is still reaching the 92% of the, compared to the reference condition. And they are having almost identical typing speed when they are used to the keyboard design itself. So my conclusion is that reduced design space, I proposed the reduced design space for the STK design, and we rigorously measured the performance of the STK by conducting series of the experiments. And with the STK, reading and typing performance are almost as fast as the reference design. So this is my conclusion. So I moved from the opaque design to the semi-transparent design, which allows users to see more contents even though the keyboard is present. So thank you, and I will take questions.
So are there any questions from the audience?
Reese Matulik, Preferred Networks. So this is very nicely and thoroughly studied, and I know you said that you only tackled text editors, but I was wondering if you have different kind of backgrounds, if the color changes, how would the keyboard adapt to these kind of changes? And the second thing, also the occlusion problem doesn't concern only reading, right? And it's also the interaction. So when I want to use my finger to scroll the text editor or to place the caret, the keyboard is occluding that space. And you've actually increased the size of the keyboard for that. So I have less space to interact with my finger. So how would you address these problems?
Okay, I will answer the second problem first. So there is obviously the interaction problem that keyboard occludes much of the screen space. So in my PhD thesis, actually, I proposed the quasi-motor interface that the keyboard is temporarily getting off when you press the key and gets straight back up when you release the finger. So in this example, the user is selecting target by activating the quasi-mode and type again. So this kind of casual interaction can actually help users and get really a positive impression from the user, even with the big amount of the screen area occluded by the keyboard. And for the first question, you asked about the various backgrounds. So I found that if you know the Photoshop, the multiply blending option, if you know that option is actually working well with the general white backgrounded area, which is common for the productive apps. And maybe we need the other approach for the dark background, but however, for the light background, we are confirmed that the multiply blending is working really well with the existing design. So I have a demonstration on my place. So if you want to test my keyboard on various backgrounds, you may come to us and test. Okay.
Are there any more questions from the audience? So I have a question as well. It's related. I had a similar question about the transition that you just mentioned, and so that's really nice. I like to see that you've thought about that. But I wonder if you've also thought about, I noticed that all the designers kind of chose to not put the keys there, but instead keep just the background. But if you do switch to just having the keys and no background, then potentially the space in between the keys could still be interactive. Have you considered having that sort of situation happen?
So the, you mean the gap between key could be penetrated?
So you can still select a cursor position or something in between by selecting in between and having a bit more space between keys.
Could be, but you know, the touch screen have a fat finger problem, which is likely to be typing the key instead of selecting the background. So I didn't thought about that option so far, but maybe yes. So this is unexplored design space of this kind of approach. Okay. Sure.
Yep. Question. Yep.
Michael Kipp, great talk, thank you. I was wondering, have you thought about warping the text in any way? Warping the text
warping.
Yeah, instead of having it linearly, so increasing the size of the caret position or the current position line, or using your nice kind of heat map to inform the way it's warped.
Yeah, I think that's an interesting approach. So yeah, it is viable to apply that warping approach to move the caret position to the comfortable places. You mean that kind of interaction, right?
Yeah, just to magnify the caret line, because that's the most you have to make up for the lower visibility, I guess.
Yeah, I haven't considered that kind of approach, but thanks for the suggestion.
Okay, yeah. Well, you have considered lots of other things.
Okay. Let's thank our